So now let's talk about how we convert analog signals to digital values inside of our microprocessor. We're doing input in this case. For example, let's look at sous vide. And this is a technique for cooking all kinds of things very precisely to a specific temperature. And the reason why I'm interested in this is because I love to cook. I cook basically every meal that we eat in our household. I'm a total nerd about basically everything, so I also love all of the little gadgets and kitchen tools and stuff like that. And sous vide is particularly attractive because it combines my love of computers with my love of eating and making food. So the way that a sous vide works is we have one of these little heating devices, and it circulates hot water around the food that we're basically cooking very, very slowly at a very specific temperature over a long period of time. So I can make a steak like perfectly medium rare all the way through without having to worry about overdoing it or underdoing it or anything like that, which is a really powerful thing when you're trying to cook and cook well. But one of the keys to this is that microcontroller, is that little computer is constantly monitoring the temperature and constantly circulating water and turning a heating element on and off. Now that heating element is just an on or off. It's either all the way on or it's all the way off, and we can deal with that. But the temperature, measuring the temperature, that's an analog quantity. And to measure the temperature of the water, we can use something like this. This is a thermistor. And what a thermistor is a temperature responsive resistor. So in this case, it's a negative temperature coefficient. That's what the NTC on the device stands for. And what that means is as the temperature increases, the resistance of the device decreases over time, right? So we can, by using the relationship between these, if I can measure the resistance of this device somehow, then I can figure out what the actual temperature of whatever the thing is. Now the challenge is that we don't have a we can't directly measure the resistance of our thermistor. It's just like a single resistor. So the way that we do it is we set it up with a voltage divider. We have a set reference resistance, and then we put the thermistor in series with that and tap out our voltage at the middle tap, and that gives us a relative voltage. And we have to do a little bit more math to get there, but we can definitely get the resistance of this device with a circuit like that. And let's look at how this works in practice. So here I've got a circuit set up that simulates kind of the behavior of our thermistor in line with our circuit. So I've got a regular resistor, a reference resistor, I've got a tap at the middle with a voltage measurement on it, and I've got my variable resistor. And this variable resistor is going to act like our thermistor. And as I vary the resistance of that device, as the temperature changes, you can see that the voltage will change along with it. So as the resistance goes up, I'll get a higher voltage at the tap. As the resistance goes down, I will get a lower voltage at the tap. So that is opposite of the sort of behavior we want, but that relates time and resistance and temperature. But I can, with a little bit of math, we can figure out what the actual temperature is. Actually, with some calibration, we can figure out what the actual temperature is and do some measurements that way. So now we have an analog voltage. How do we get this analog voltage to be a digital value? There's a couple of ways to convert analog to digital information, and this is one of them. This is called a flash analog to digital converter. And basically what it does is we have a giant resistor ladder like the one that we had in our digital to analog converter, and in between each resistor and our input we have a comparator. And this comparator says if this voltage is above or below the input voltage, I'm going to set myself to 1. And then we have some logic that combines them. So as you can see here, as the voltage rises for each of these, for this input, as it goes through the spikes, the different outputs are turning on and off and immediately converting the analog voltage here at the input into the encoding for that value, right? Which is really cool. Now the problem with this is that it takes up a huge amount of silicon. Each one of these is an operational amplifier. There's a bunch of resistors, and I've only got the 8 of these things here. I'm only doing 3 bits of resolution, so that gives me 8 different configurations that I need to verify, right? Now, if I wanted to do 12 bits, I would have to have 2 to the n, where n is the bits, comparators and resistors. I would have to have every single possible level built out, and that gives me a real headache when I'm trying to design my chip. That's a huge amount of space that I can't use, that I may not be able to have. However, this is super efficient. It's very fast to convert. It's basically as soon as the electricity can propagate, I can have a digital value on the outside that gives me a high or a low, or a 1 or a 0 for that encoding. Let's look at a different approach. This is a successive approximation approach, and here we have one single comparator and we have a bunch of voltage sources, the same as before, but instead of doing it all at once, the computer actually goes through and does a binary search for whether the voltage matches or not. So in this case, whether we've exceeded a reference voltage or if it is doing the opposite, right? So here, basically what this signal is saying is I'm comparing my input value, which is this 2.8 volts, with my reference, and I'm going to try a bunch of references until I'm below this thing. So I can start from a high value. I can start from like 1, 0, that's my digital value, and I can see it went to 0, so I'm above that. If I that's too high, and then I can try 1, 0, and I'm below that. So in between the two somewhere is the value that I'm looking for. So that is how I can do it. And because I'm doing it literally by most significant bit down to least significant bit, I'm basically doing a binary search through the space of these things. But I'm taking my conversion from being very large and space inefficient to being small and time inefficient, right? So now I have to take time to do the conversion. And this is the kind of analog converter that we have on our ARM board in this class. So to set up the analog to digital converter on the ARM, I'm going to leave it again up to you to figure this out. I want you to read through the data sheets, and the quiz will sort of lead you through some of it. The analog to digital converter is way more complicated than the digital to analog converter, so we're going to talk about it a lot in class, so be prepared for that.